Loading. Hi, everyone. Welcome to another JakartaOne Livestream Cloud Native for Java session. I hope you have been enjoying this event as much as we have. And for this session, we have Dr. Clement Escoffier, and the topic of his presentation is bringing Reactive to enterprise developers. So please take it away, Clement.
Thank you. So welcome to this session. My name is Clement Escoffier. I'm doing reactive stuff at Red Hat. And today I'm going to specifically talk about Quakers and how in Quakers we are unifying reactive and imperative to ease reactive to enterprise developer. This is JakartaOne, so I believe that most of you could be qualified as enterprise developers. So I will show you what you could or can do already with some reactive superpowers. But the first thing is, what does reactive mean? So I do reactive things for the last 5 years or so, a little bit more than 5 years. And I got this question again and again and again. And the second question that comes always or very often is, do we need this new thing? And actually things are changing fast, and yes, and let's see why. So first thing, what does reactive mean? If you look inside the Oxford Dictionary at this URL over there at the bottom, you will see that reactive is defined as follows. Being reactive means showing a response to a stimulus. Okay, we can do something with that, but there is a sub-definition which is much more interesting for us. It means acting in response to a situation rather than creating or controlling it. That means that you are not in control of the flow anymore. It's the stimuli that come from your neighborhood that will tell you what you need to do. So what are those stimuli? It can be failures, message, errors, and so on. So taking these two definitions, and let's try to apply them to software, we can make up another definition. Let's say that a reactive software is an application reactive to stimuli such as user inputs, messages, and failures. And then you say, well, this is not new, right? This comes from the 60s. This is actually event-driven. And yes, reactive and event-driven have a lot in common. So when you build a reactive applications, you are going to receive and send stimuli that can be events, signals, failures, whatever. So what's new? Because, well, this, you can already do it with your current Jakarta EE or Java EE technologies, right? You can use the GBs, you can use message-driven beans, you can use CDI server to do exactly this. So what's really new? Why do we make so much fuss around reactive? So the thing is, reactive comes with a different concurrency model. And at the bottom is the idea of using non-blocking IO. Why? Because we need to use more efficiently the resources that are given to the application. We're going to see why in a few minutes. So in the Java world, there is one non-blocking IO toolkit that really dominates. It's Netty. It's awesome, really low level, but yeah, most of the reactive frameworks that exist in the Java world are based on Netty. On top of that, you have various reactive frameworks that will, let's say, make Netty a little bit more bearable for bare human. Again, it's really low level Netty, so it will abstract a little bit, and then you have your application code. So the thing is, because it uses non-blocking IO, it will reduce the number of threads to almost nothing, so 1 to 4 threads, and your application code may be executed in these IO threads. So it's very efficient, but it comes with some reality. You must never block, because if you start blocking, you are blocking the IO threads, and you are going to kill all the benefits of reactive. So for this, you need to write your code using asynchronous development model like callbacks, reactive programming, coroutines, and things like that. It's not that simple. We are going to see some example on how we try to improve it. Reactive is not only about one application. It's also about distributed system and applying the definition we have seen in the first slide to a complete systems, meaning that we are going to exchange events, we are going to exchange stimuli, and our system is going to react to that. And on this slide, you say, yeah, but that's microservices, and we are doing monoliths. It's actually not about microservices versus monoliths versus application versus service. As soon as your application is interacting with something outside of the process boundary, it's a distributed system, and you are in this scene. So call it as you want. There is no consensus about how it should be called, except, well, it's a distributed system. And there is no better definition of a distributed system than this one from Leslie Lampard. And it can be summarized very simply. It's going to fail. You can be a genius, it's going to fail, and failure will be part of the game. So you need to embrace the fact that failure will be there. They are first-class citizens, and actually, on large systems, failures are more common than expected outcome, which is kind of weird. Interesting enough, everybody wants to build distributed system. While it's very, very challenging and very, very hard, Reactive try to make them better, more reliable. Building reactive systems mean building a better distributed systems that focus on responsiveness. And why? Well, it's a little bit Google's fault, in the sense that a few years back, no problem. We can do slow things or rebooting things at the middle of the night, no problem. But now, everybody has used the Google experience. It always works, it's blasting fast, there is no problem on availability, it's never failing, and we need to approach the same kind of user experience. And this user experience, that means being responsive. For doing this, in our reactive systems, we are going to use messages and having elasticity and resilience pattern. The message here, this message word is key, because basically what reactive systems is all about is about exchanging messages. So your distributed systems is going to use to exchange messages. Well, today, if you're building microservices or distributed systems, there is a good chance that you are using HTTP. And what's wrong with HTTP, right? So the thing is, you can use HTTP and JSON or REST or whatever. You believe that you have implemented loose coupling, but actually no, you are using strong coupling. It's not about the format you exchange, that's just the first part. It's about uptime. Meaning that if you use some synchronous interaction with request reply, you need to have both ends of your interaction at the same time. They're alive at the same time. And it's not only those services, it's also all the infrastructures and so on. So there is really uptime coupling, which means that if one of your service fails because it's synchronous, the caller is going to fail, the caller is going to fail, and the caller is going to fail until you get the users. Well, and unhappy users, because again, remember the Google experience, it must always work. So you can say, well, but a few years ago, Netflix have repopularized circuit breakers, and repopularized is the right word because they didn't invent it. They existed since the 60s, and they're very efficient in some cases. So what's a circuit breaker? A circuit breaker is just an object that is going to monitor the interaction between two services. Let's say A calling B. So it's monitor when A calls B, and according to the number of failures per unit of time, it would decide whether it's worth to call B or just inject a fallback or things like that. So it's come with retry and auto recovery mechanism. So it's very, very nice. Tricky thing, tuning circuit breakers is a nightmare. And the thing is, circuit breakers are not really made for the world of the cloud in which we're living. In the sense that A and B, A calling B, but how many instances of B do I have? And where is B? If I have a single instance of B, okay, I can define my timeout, I can define my latency and the number of failures. Okay, that I can define. I can customize that. But let's imagine that suddenly I don't have one instance of B, but 5. That changes a lot of things then, because if I have 5 instances of B, then it may react much more quickly. And maybe the instances of B are not in the same data center. Maybe one of the instances is in my data center, but the other instances are in another data centers. In that case, how can I quantify the time, the latency, and so on? And this topology is going to change dynamically, and that's the beauty of the cloud. But unfortunately, in that case, circuit breaker is not great. So what's the solution? Well, I spoiled it a little bit a few slides ago. It's called messaging. Messaging exists since the 80s, probably 70s. And the idea is instead of calling B, I'm going to send messages to a virtual addresses. And then I can have one instance of B, 10 instances of B, even instances of C. If I'm using a pub sub or publish subscribe, I don't care. The sender, I'm really low scoped here. When I'm going to send messages, I'm going to use non-blocking message spacing, no problem with that. Elasticity comes from the fact that the number of consumers behind a virtual address can evolve over time. I can have 1, I can have 2, 3, and so on. I can even go back to 0 because most of the message middleware today implements some kind of durability, which means that even if I don't have any consumers at that time, no problem, the messages are not lost. As soon as one arrives, the processing will start. This is quite powerful. Resilience also comes from the fact that you can have multiple consumers, because if one failed, another one can take over and continue the processing. Also, message middleware comes with retry and acknowledgement policies that let you easily implement any kind of fault tolerance. The thing is, when we talk about messaging to enterprise developers, they say, oh gosh, GMS again? And there is one thing in common between GMS and CORBA. We still have scars all over our body and brain, and we really don't want to reuse those APIs. They didn't age well. And we will see later how, thanks to MicroProfile reactive messaging, we make the development of such kind of system really easy. So again, by using messaging, it's easier to implement what we call a reactive system. So reactive systems are distributed systems with these 4 characteristics. They have been defined by the Reactive Manifesto. You can Google these terms. It's a 4-page document that is very well written and explain how to build such kind of systems. And the core idea is to use asynchronous message spacing. Thanks to this, as we have explained in the previous slides, it gives you elasticity and resilience, and so you become responsive. Because you can continue under the load, under the request, under the messages, even under fluctuating load, and even when facing failures. So you improve the user experience. You answer in a timely fashion. You embrace the dynamism of the cloud and the failure that are natural in a distributed systems. So one key aspect of this is that asynchronous message passing doesn't mean multi-thread. It means actually the opposite. And reactive doesn't mean multi-thread. If your reactive a client or framework is actually just a broken layer on top of a thread pools, you do it wrong. Reactive is about never ever block. Why? Because remember what we had at the beginning with this IO thread. That's this key. So why there is multiple benefits on being reactive and never block, but let's see one today. Containers. Containers are not about isolating applications. Actually, absolutely not. They are not been made for that. Containers are about sharing and increasing the deployment density, which means that on the cloud or on your private infrastructures, there is CPUs and memories somewhere. This is virtualized to you, but yes, somewhere there is physical CPUs and memory. Then you have a container host on which you will deploy containers. If some of your containers are using a regular approach with one thread per request and things like that, then your level of concurrencies is limited by the number of threads from your thread pool. The issues is with the number of requests per second that increase because of mobility or IoT and things like that, you need more and more threads or you need a second instances of these containers. Each thread costs memory, around 1 megabyte. It depends on many things, but it's around 1 megabyte. So a lot of threads cost you a lot of memory. So if you start a server with 100 threads, you will use 100 megabytes of memory. which means that the other containers cannot use this memory because it's used by the first containers. A hidden cost of threads is CPU cycles, because more threads you have, more time you are going to spend switching between threads. Even if it has been really optimized over the past years, it's still not zero, and more threads you have, more wasted CPU cycles you are going to spend. You can say, yeah, but no problem, we can use quotas. Okay. The tricky thing with containers and quotas is that as soon as they reach the limit, they just get killed by the container host. That's the poor life of containers. And while we all did that, we all had containers that reach the limits and it's been killed. And what do we do in that case? Well, that's simple. We call the admin and say, hey, can you increase my quota? Which is actually the opposite of what needs to be done, but it's what we do because we're human. So by using a reactive approach, we kind of improve this because we can reduce the number of threads. You don't have to be all in on reactive. You can mix reactive and imperative and use reactive for common roots, common endpoints that are really called a lot, and the traditional approach, imperative approach, for everything else where you really need transaction and things like that. Where we'll see how it can work all together. So, but first, let's look at some pragmatic questions because I talked a lot but didn't really show you anything yet. So these questions have been collected over the past 2 to 3 years when I was presenting Reactive to many developers, customers, and different companies. So the first thing, and one of the questions we often have is, yeah, okay, being Reactive, it's all about being asynchronous, so I can just use completion stage. So there is some kind of love-hate relationship with a completion stage. The tricky thing is, so first, completion stage, you may use it on another name, which is completable features, which is the main implementation. Completion stage being the interface. The tricky thing with completion stage is the API. It's kind of nothing similar to that in the JDK. So it comes with a JDK, but it's kind of a weird beast. That's something that has not been integrated with the rest. So it's really new API. The thing is, this API can be very confusing. You have then apply, then accept, then compose, and some of the methods are suffixed with async. But well, isn't completion stage all about async? So why those methods are async? What about the other one? And what's the difference between an async method without an executor parameter or with an executor parameter? It's really confusing. And what we have realized over the past few years is actually create more confusion than anything else, especially when using an async method without an executor in a container. This is just a ticking bomb. So to avoid that, in Quakers, we are introducing a new reactive programming library, which is named Mutiny. And instead of completion stage, we are now recommending Uni. Uni is something, it's kind of representing an asynchronous operation, but it's lazy. So that means that you need to trigger the computation explicitly. Returning a completion stage means that the computation has already started. With Uni, it's not the case. And it's much more event-driven with on item, on failures, and things like that. So it's much more, it's easier to write, and the API is actually more compelling. How does that work? Well, if you use Quakers, that is going to be like this. So you can, in a JAX service endpoint, return a Uni. And this means that this endpoint is going to be asynchronous, which means that we are going to pause the request, wait for this Uni to redeem its item. And once it's ready, we will resume the request and write the response. You can use that with a MicroProfile REST client too, by returning a Uni. So that means that it's still an HTTP call, but it's going to be handled completely asynchronously using a non-blocking IO. And when you get the response back, we can continue the computation. So it's already one step to asynchrony. It's not totally perfect. We will see why, but it's already one thing. Uni are really made for one item or one failures, but sometimes you need more than one. You need streams. For this, in Mutiny, we have a second type, and we only have two types, uni and multi. Uni, it's one item. Multi is 0 to n items. It can be unbounded. Both are lazy, using a subscription mechanism. So if you use Reactive Streams or with Java or reactors, that's the same ID. On multi, we have a request protocol too. We are going to talk about that when we will mention back pressure. And it has almost the same set of operators. So it's come with a very rich set of operators that focus on the expressiveness and not on mathematical concepts. Back pressure is a key aspect on a multi. Because on a uni, when you say, okay, I really need your result, that means that you're ready to retrieve the result. On a multi, you don't know in advance how many items you can get. So this has an impact and an issue, because if you have a fast producer and a slow consumer, well, that means that very quickly the slow consumer is going to be overwhelmed and may die out of memory or something. It becomes very slow, so it doesn't work and may probably break your complete systems. So you don't want this. So in Mutiny, we implement the Reactive Streams protocol, which actually is very simple. The slow consumer is going to request the producer and say, okay, I'm ready. I can handle 2 stones. And the first producer can send 2 stones, maybe asynchronously. So the first one, and when the second one is available, then the second one. So we never overwhelm the consumers. And thanks to this, we can actually self-pace our system very, very nicely. Another benefit of this is monitoring. It's very easy to detect bottlenecks, because we just monitor how many requests has been done and say, hey, look here, we don't do a lot of requests, so that means that this consumer is slow, or this producer has received lots of requests but cannot fulfill them. So what's wrong with the source of events? So, and by doing this, you can really tune your systems correctly. So when using multi, again, in Quakers, that's going to be very simple. In your JAX server endpoint, you just return a multi, and it's streamed to the client, or using SSC, and then it's an SSC response to the client. The tricky thing is that how do I get those multis? And I don't know if you heard recently, but there is something very, very common or very popular these days. It's Kafka. We heard a lot about Kafka. Many people are now using Kafka as a cornerstone of their systems. But a lot of people say, oh, because I use Kafka, I'm reactive now. I'm becoming event-driven. That's not necessarily true, but used correctly, yes, Kafka will give you those reactive superpowers. So let's see how it works. But actually, the thing is not about Kafka. It's about any message middleware like AMQP, RabbitMQ, MQTT, or even GMS. As I said, when we mention GMS to enterprise developers, they say, nah, we don't want to really use this again. If you compare the API with the Kafka API, it's not really, well, it's different ages, different period of time. So how can we do that? We would need a development model which is much closer to CDI, or maybe even a CDI extension. And this is exactly what we are doing with MicroProfile reactive messaging. So you can imagine receiving an HTTP request, get through Quakers, get some application code, and this code can say, hey, I want to send a message now. And to do that, what we will do is that inject an emitter, and this emitter is going to send the message that will go through Quakers and back to our MicroProfile reactive messaging, which will connect to the messaging middleware, send the message, and then on the other side, I receive the message and go and back. But we really want something natural for enterprise developer from the CDI developer point of view. So to demonstrate this, we are going to use the coffee shop example. So I don't know where you're living, but at least in France, we are not officially in lockdown anymore, but bars are still, and pubs and coffee shops are still closed, which is a nightmare. But anyway, so here we are going to see two generations of coffee shops. The first coffee shops is going to be a old school coffee shops where I go to the bar, I go to the bartender and say, okay, give me an espresso. And the bartender go to the coffee machine, prepare my espresso, give me my espresso, and I got my espresso. The tricky thing is that during that time, several customers have queued and he was unable to serve them because he was serving me. Really blocking approach. There is another type of coffee shop, generally American chains, where you go to the bartender, you order, they ask for your name, they misspell it, they send that to a barista, and then they say, oh, go over there and we will call you when your beverage will be ready. It's kind of weird, but the tricky thing is that while I'm waiting over there, they can take other orders from other customers. And this is actually quite interesting how it scales, because that's you can have more baristas and things like that. So the demo I'm going to show you, you can get the code at this URL over there. It's the code that I'm going to write in a few minutes. I'm using Kafka because I want it to be cool and it's rarely used these days, but you can use it with any type of messaging middleware. And actually, you will see in the code there is nothing Kafka specific. So let's have a look at this. Okay, up. Here. So this is my coffee shop UI. So, and I'm using the whole coffee shop. So using HTTP, I enter my name, and I will order a Frappuccino. And you see, while one is ordered, I cannot place another order because it's blocking. And it's exactly what we don't want. So, but this Frappuccino has been prepared by Shirley, and yes, so and something I forgot to mention, there is some random time to simulate how it works. If we look at this code, it's done like this. So this is my coffee shop resources from my Quakers applications. Oh, by the way, I mentioned JackService a lot, but here I'm using Spring, right? So Quakers come with a Spring API compatibility layer, so you can actually mix both, use Spring API, use JakartaOne or MicroProfile APIs, or mix both, and we're going to do that in a few minutes. So here I have my barista service, which is a MicroProfile REST client. Again, it's asynchronous. It returns a uni of beverage, okay? And if I go back there, when I was clicking on the button, this is called on /HTTP. It gets the order, sends the order to the baristas, and then send it back. So I'm using Uni here, so that's asynchronous, but yeah, it's still HTTP. And if the barista is not there, actually, we can try that very quickly. If I kill my barista and I try to place an order, then I get an error immediately, because of course, it's HTTP, so both ends must be alive at the same time. So let's switch back to the code and see how we can use Kafka for that. So when I will switch the types, I will call this route here. And this route is going to not send a single event, but 2 events, and we will see why. So to send events, I need an emitter. So I'm going to inject an emitter that will send an event or a message on a channel. MicroProfile reactive messaging is using the concept of channels, and channels can be mapped to Kafka or whatever, or even in memory. So here I want to send a message on the orders channel, and I will call that, so it's an emitter of order, and I will call this one orders, okay? Then I will create another one on the queue channel that will get beverage, or at least status, and I will call that queue, okay? And here in this method, I will first send a message to the queue channels, and that is going to be beverage.queued, just saying that we have received your orders. We will call you when it will be ready, and we will send the order to the baristas, saying, well, you need to start preparing this order. That's it. So if I go back here, I will refresh to have a clean. Yes, it's clean. I switch to messaging. I will give my name that they will misspell it. Let's say like this. And I'm going to start having try, and I enqueue try a lot. And let's see. So Ava, so it's a Kafka barista, is starting to receiving order and prepare them. And then you say, hey, what about ordering? So this is Kafka specifics, and you will need to read a lot more about Kafka to really get the order right. But it's about partitions and keys and things like that. And here I've simplified it. So how does that code work? Because we have seen this side, the coffee shop, but what about the barista side? This is going to be my barista side here. So it's another service running in another process, and it uses a different set of annotations, but very simple. It means that this method is going to be called for every orders transiting on the orders channels, and the response is going to be written on the queue channels. So here I'm using a synchronous method, and this synchronous method that is here is actually going to call sleep to simulate that it takes time to prepare a good coffee. So because this will be blocking, and blocking is actually not really reactive, you will need to say, oh yeah, I know, it's a blocking call, so call me on a worker thread. And everything here can be configured to control the concurrency and things like that. Of course, this is one type of signatures we support, but MicroProfile reactive messaging support more than 30 different types of signatures. You can have asynchronous processing, non-blocking processing, stream processing. You can use actually reactive streams objects like publisher, subscriber, processors directly. So we provide you a lot of things. This is actually one of the simplest we have, and that's the first step to reactive. And then people start to remove the blocking things by doing this one in an asynchronous manner. Okay, so what does that bring us? Because right now we don't really see the benefits. So let's imagine that my barista is taking a break. So I'm going to stop it. And I'm going to start ordering hot chocolate. So while with HTTP, it was failing immediately, here, well, it's not lost, which means that as soon as I start another Kafka barista, it's going to start the processing of these pending orders. And look at how fast it was to start a Kafka barista. This is the magic behind Quakers that has been compiled into native that make it very, very fast to start. And now we have George that is preparing my hot chocolates. So, but what happens if I really, really want a lot of espressos? Really a lot, like 100 of them. Really a lot. So George is ready, he can start doing that, but we may help him. And by starting the second barista here, which is in Java mode, so you can see the difference of starting, we should get multiple baristas to handle the load. So will we get? No? Groups. We need more. Let's do more then. Still only George. So Oliver is back. So it happens sometimes that actually my two baristas, the names is picked randomly, and it happens that sometimes I pick the same name, random. So it's hard to follow. But here we have now George and Oliver that are sharing the load and can get my tons of espresso much faster. So let's go back to the slides now. Here. So the question here is, did we implement reactive systems? Well, and if we do, it should not be so hard, right? What did we use? We used an emitter that is injected with @inject, so you should be familiar with this. And on the other side, two annotation, @incoming and @ongoing. Oh yeah, and something I forgot to show you, sorry about that, is how it's configured. Because basically each channels can be configured to Kafka and QP or whatever. And this is how it's done using MicroProfile config. You say that the orders channels is handled by this connector. So here it's a small white Kafka connector, and this will be my serializers, and so on and so on and so on. So it comes with sensible defaults, but everything from the Kafka configuration point of view can be configured. So, oops, where is my slide? No.
Okay, looks like Clement got disconnected and is trying to reconnect. Let's just give him a few minutes to connect back. And there you are. You got disconnected, Clement.
Yeah. So let me reshare quickly. Sorry about that. So sorry about that. Is it back online? Yes.
Yes, you are. I can see your screen.
I closed the wrong window, and that was the windows that we should not close in such kind of virtual events.
Don't worry.
So the question here now is, did we implement reactive systems? Well, yes, because what we have seen is if we don't have any baristas, or if one failed, then it's not a problem. Our orders are not lost, and I will still get my coffee. And so it's actually key here, because even if we have no baristas, we keep them. And as soon as a barista comes, it will start processing my coffees and my orders. The second point is, what about in terms of elasticity? Well, we have seen that I can start a second baristas, and they get the load shared among George and Oliver, if I'm not mistaken. So it's quite nice. So of course here I've explicitly started the second barista to show you for demonstration purpose. But if you are on the cloud, you are going to monitor the number of pending orders, and according to this, you are going to scale up and down. If you use things like KEDA, Kubernetes event-driven architecture, then this is all done for you, and you don't have to do anything except saying, okay, when the depth is 10, then start a second consumer, something like this. So we did implement our reactive systems, and relatively easy. So how does that work? Well, we have seen a few things in this demo. First, we have seen a little bit the developer joy. I was able to write some code, refresh, it was there. We have seen the supersonic subatomic Java from Quakers, where it can start very quickly with a low memory. So that makes it cloud native, but to be really cloud native, you also need to use efficiently resources, and this is all about reactive. And today we are focused on the unification of imperative and reactive, but there is a thread behind this. How is that done? If you look at Quark's code or look under the hood, well, you will see that actually Quark's has a reactive core, and everything you do is going through this reactive core. You write a JackService, a traditional JackService endpoint, or even a servlet, is going through these reactive engines and will get dispatched to your servlet or JackService. This engine is based on Eclipse Vertex, which itself is based on Netty, and Vertex has been battle tested over the last 5 years, so we know exactly how to tune it, and it supports almost everything you can imagine. So how does that work? We get an HTTP request, for example, it goes through Vertex, so it's a Vertex HTTP server that get it. It goes through a routing layer that will dispatch or find who is going to handle this request. If it's imperative things, it will call it on a worker thread. If it's a reactive things, it can stay on the IO thread. So it's really interesting. But why it's so interesting to have both? Because let's imagine you have a service and you realize that, yeah, you could increase the concurrency by moving this endpoint that is called a lot to be reactive. You don't need to do okay, let's go all in reactive and re-implement everything reactive. That doesn't really work. Here, you can actually have both. And step by step, you can move all to reactive or even keep both. There is no problem in keeping both. And on the reactive side, you have all the messaging things that we have seen today. We have reactive routes, which are kind of JAX-RS, but dispatched on the IO thread. And we have a lot of things around reactive data access to being truly non-blocking and reactive to connect to Postgres, MySQL, MariaDB, Mongo, and so on. And I will say truly non-blocking means that there is no pool behind it. It's really directly as a protocol. It's at the protocol level, it's non-blocking. There is no thread pool. So it has been a challenge in Quakers to achieve this, but we're really, really happy, and we have plenty of things to deliver in the next few weeks and months. We are adopting MicroProfile specification and some Jakarta E specifications, and we incubate some experimental features like this ad blocking. It's actually something that is incubated into a small Y, and if it works well, and once we have really better understand how it's used, we are going to contribute that to the spec. That's all I have for you today. If you're interested by Quakers or by everything I've said, you can go to the quarkx.io website and you will find plenty of documentation. You can even go to code.quarkx.io and start your project right away. Quakers is not only innovating on the technologies, it's also innovating on how you interact with the team. And if you never use Zulip, it's pretty good, but the first week is a lifetime experience. It's it's great. You will see. It's like Slack, but with 10,000 more notifications per second. You will love it. You can follow us on Twitter, and also if you like Quakers, if you say, hey, that's pretty nice and so on, go to the GitHub page and give us a star. It's totally useless, but that makes us, the Quakers team, quite happy. Thank you, and if there is any question, I have a few minutes to answer them.
Yes, thanks, Clement. So we have one question. How do you test reactive stuff?
That's a great question. How do I test it? So actually, I said that blocking is not allowed inside your applications, but in test, it can be allowed. And when you retrieve an asynchronous uni, for example, you can block to get the result. But blocking is not hidden behind a join method or get method. It's clearly saying, okay, I got my uni, and I will call await dot indefinitely. So actually, can I go back here? I'm going to here. Yes. So something I could do here. So it's not going to compile, but if let's make it a uni here, and if I want to have a blocking result, I just do wait indefinitely. And here on, of course, you can have a timeout and things like that. So that's how we test it. We also provide a few test utilities like test subscribers and things like that to verify all the events that have been received and replay them. So we provide a lot of things around this. For reactive messaging, how do I test Kafka and things like that? We provide an in-memory connector, which actually lets you inject messages and check what is received. So inject messages to channels and check what has been sent to another channel. And so you can write it like that without having to start Kafka or MQP or anything else. It's what we call an in-memory connector. So, and you switch. So your application is developed against Kafka, and you just use in-memory connector that switch these channels, and you're done. So all this is documented, so don't worry. You go to the quarkx.io website, you look for reactive messaging or mutiny, and you will find everything I just said about testing. And there is more things to come, and if you have more ideas, feel free to ping me, and I will be very happy to discuss that with you and maybe implement that.
Steve, we have two more questions. Are plans for gRPC support?
Also, okay, so let me answer this one. So yes, we have planned for gRPC support, and I spent the last 2 weeks implementing it. So believe me, it's hot, fresh, and it's going to really be cool. It's going to be released with quarkx 1.5, which will be released beginning of June. The exact date should be June 2nd, but you know how it works with releases and estimate and developers. It can be a little bit after that, but yeah, first week of June.
All right, great. So the next and last question that I can see is, what is your suggestion for a developer from synchronous tech learning better asynchronous way?
So I have trained a lot of developers to Reactive over the last 5 years, and we came up to realize that it's hard. For us, as we were living in, it's easy. And what we try to do with Mutiny, which is a new reactive programming library, which is not as known as Reactor or Reactive Java, is to actually make it much more simpler for regular traditional developers to use it. And it actually works. We had a couple of developers that have started it that we don't know. We didn't train them. We didn't give them anything and say, hey, that's pretty cool. I wrote my first Reactive microservices, and I didn't know anything about Reactive a few hours before, and they were all about to do that. So the idea is to really shift to say, okay, I'm going to receive events, and I need to decide what I will do on each event. Once you have this, and you can write that down on a piece of paper, then with Mutiny, it's going to be very, very simple to implement. We are coming with a lot more resources to learn such kind of things. We already have plenty of them in the Quakers IO website. I have a few presentations that are going to be recorded later this week. Not JakartaOne, unfortunately. There is other virtual events. So stay tuned, and we are going to give you everything you need to start learning Reactive. But yeah, don't start with highly complicated reactive programming libraries. You can write the code and say, hey, I wrote this. It's pretty nice. Look, I use flatmap, matplotlib, and so on. And 1 week later, say, oh, by the way, what the code I wrote? What does it do again? So that doesn't really work well.
And yeah, we have one more question. Do you know if Mutiny is being considered to be part of the reactive specification in MicroProfile or Jakarta EE?
So initially in MicroProfile, we were working on another specification named MicroProfile Reactive Streams Operators that was using compression stage and reactive streams directly. It was a great way, a great integration layer, but the usability was not good. Before becoming a spec, we need to have feedbacks, and Mutiny has been released in December. We start having feedback, and really good one. I'm very happy about that. There's still some work to do. It's not complete, and we want more feedback. And yes, maybe at some point, let's say in 6 months or to 1 year, we will start discussion and say, hey, is MicroProfile interested to write a specification on top of that? We actually starting discussing this actually after the first few lines where we started writing mutinies to say, while we are working, we're a little bit changing the direction. We want to try something, and maybe it will become a spec. Maybe it will replace the current one. So yeah, eventually, but I cannot tell you when, and I cannot tell you under which form or under which specification. I hope so.
All right. Thank you so much, Clement, for your great presentation. It's great to have you on our Cloud Native for Java event. And so we have around 11 minutes for a break, and then we will see you for the next and last session of this event. So thank you very much, and see you soon.
Yeah, so thank you very much, and sorry to have closed the wrong windows. I hope that, I was able to recover nicely. So
don't worry.
Failure of the first-class citizen. See, I'm a distributed system. I failed every single day. Okay, thank you, and have a great rest of the conference.
Thank you. Bye.
Bye.